Triple integrals in cylindrical coordinates. The cylindrical coordinate system is very similar to the polar coordinate system. In the polar coordinate system, where we're just looking at the x and y axis, we know that if we have some point xy, we can represent that in polar coordinates by defining x to be r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. The only difference between polar coordinates and cylindrical coordinates is now we are going to come out of the xy plane to a particular point on the z-axis. So cylindrical coordinates has an x and a y coordinate exactly similar to the polar coordinate system, and we define z to simply be equal to itself, z. And so a point in polar coordinates has coordinates r, theta, and z. Let's consider the following example. Plot the point with cylindrical coordinates 2, 2 pi over 3, and 1. And find its rectangular coordinates. So I will attempt to do this. We have an x-axis here, we have a y-axis here, and a z-axis. And we are graphing the point r equals 2, theta equals 2 pi over 3, and z equals 1. So r equals 2 means that we're going to come out a distance of 2 units, but then we have to rotate through an angle 2 pi over 3. So rotating from the x-axis in the direction of the y-axis, pi over 2 would be here, 2 pi over 3 would be an angle back here. So if we continue the x-axis in this direction, the angle 2 pi over 3 in the xy plane looks something like this. So we are going to go on that angle now 2 units out. And so 1, 2. And then finally we have a z-coordinate equal to 1. So if this is equal to 1 on the z-axis, we are simply going to come up a distance of 1 unit there. And that is the approximate location of that point. Now in terms of giving the rectangular coordinates, we know that x is equal to r cosine theta, r is 2, theta is 2 pi over 3. This is going to be 2 times negative 1/2, which is negative 1. And y is equal to r sine of theta, which is 2 times the sine of 2 pi over 3, which is 2 times the square root of 3 over 2, which is radical 3. And so the point can be written in rectangular coordinates, x, y, z, as the point negative 1, radical 3, and then remember, z is still equal to 1. Now for part B, it says find cylindrical coordinates of the point that has the following rectangular coordinates. So here, we're just going to recognize that x is equal to 3, y is equal to negative 3, and z is equal to 7. Negative 7. All right, the way to do this, in my opinion, is to just go to the xy coordinate system, and we know that the point x equals 3, y equals negative 3 would be a point in the 4th quadrant. And we should know that the angle associated here is 7 pi over 4, right? Because we know that this reference angle here is 45 degrees, or pi over 4. And so this angle is 2 pi, take away pi over 4, which is 7 pi over 4. We also know, if we zoom in here and create a right triangle, this side has length 3, this side has length 3, and since this reference angle is 45 degrees, we know that the hypotenuse here should be 3 radical 2. And so that's the value of r. So we have r equals 3 radical 2, theta equals 7 pi over 4, and of course z is the same, which is negative 7. So in polar coordinates, we have the point 3 radical 2, 7 pi over 4, negative 7. Now, I should also remind you that this is not a unique answer because the angle here can be any angle that is coterminal with 7 pi over 4. So I can replace 7 pi over 4 with 7 pi over 4 plus 2 pi times k, where k is equal to any integer. Also remember that if I wanted to express the angle over here, I could do that, right? So that angle would be 3 pi over 4. But if I did that, then r would have to be a negative number. And so r would need to be negative 3 radical 2. So there are infinitely many possibilities of cylindrical coordinates when you're given a set of rectangular coordinates. We can also think about graphs in cylindrical coordinates. So if we are in the cylindrical coordinate system and we have the equation r equals c, that simply means that r is equal to some constant c, theta can be any angle, and z can be any value. So if you think from the positive x-axis, if we can rotate to any angle, but r must be c units from the origin, then you are going to get this circle here. And then because z can be any value, you can get any value above or below that circle, and that makes this cylinder. An equation like theta equals c refers to theta being a constant. So if we rotate through some angle theta, which is equal to c, we are simply going to get the plane at that angle. And this is because z can be any value and r can be any value, but theta has to be that angle. And finally, if z is equal to a constant, that's the same graph as it's always been. That is just a flat plane parallel to the x-y plane at some constant z equals c. So let's consider the following example. Describe the surface whose equation in cylindrical coordinates is z equals r. So let's just remember that if z is equal to r, then that means z is equal to the square root of x squared plus y squared, because we know r is the square root of x squared plus y squared. And that means that z squared would be equal to x squared plus y squared. And this gives us a cone. And actually, I should mention up here, when we first put it in, we would put a plus or a minus there, because remember, r now can be positive or negative. But this is going to give us a cone. So whatever you plug in for x and y, z is going to be the square root of the sum of the squares of those things, but z can be positive or negative, and so that is going to give us a top half of the cone and a bottom half of the cone. To perform triple integrals in cylindrical coordinates, it is very similar to the polar coordinate comparison. So in polar coordinates, you might remember that dx dy got replaced with r dr d theta, but now we also have to contend with the variable z. But remember, z stays the same in cylindrical coordinates. So really we are just converting x and y to r cosine theta and r sine of theta respectively. So what you're going to have here is the function replaces x and y with r cosine theta and r sine of theta. Dx dy becomes r dr d theta. We have our dz, which is there to begin with. And then when you integrate with respect to z first, z is going to be transformed into some function of r and theta. So here's a picture of what that would look like here. But it's best just to do an example. So here we wish to evaluate the triple integral over the region E of the function x squared, where E is the solid that lies under the paraboloid z equals 4 minus x squared minus y squared, and above the xy plane. So let's think about how this would be done in rectangular coordinates. We would integrate x squared first with respect to z, and z is going to go from 0 to 4 minus x squared minus y squared. Then we would integrate with respect to y by projecting this region down onto the xy plane, which is simply a circle of radius 2, and that is going to have limits negative square root 4 minus x squared and square root 4 minus x squared up top. And then x simply goes from from negative 2 to 2. And of course, we could do this integration, but this would be rather complicated, especially in the second integral. So instead, what we can do is we can change our function here to a function of r and theta by making the simple substitution x equals r cosine theta. And so if we plug that in here, we are going to get r squared cosine squared of theta. Then we're going to have the integral with respect to z, and z goes from 0 but up to 4 minus x squared minus y squared. That's the same as 4 minus the sum of x squared and y squared, which is 4 minus r squared. And then dy and dx gets replaced with r dr d theta. R is going to go from 0 to 2, and theta goes from 0 to 2 pi. Now, of course, when we do this, we need to put this r over here. And so that's going to give us this, and then we are going to integrate with respect to z. And so we have the integral from 0 to 2 pi, integral from 0 to 2. Integrating this with respect to z gives us r cubed cosine squared of theta times z from 0 to 4 minus r squared. So that's the part we need to focus on now. And then, of course, when we're done, we'll have our dr d theta. So plugging in 4 minus r squared for z gives us r cubed times 4 minus r squared times cosine squared of theta. Integral from 0 to 2 dr, integral from 0 to 2 pi d theta. Next, we'll go ahead and multiply this out, and let's go ahead and do this step right here. So we have 4r cubed minus r to the 5th, and that's multiplied by cosine squared of theta. With respect to r, cosine squared of theta is a constant. And so the next step here is we're going to integrate 4r cubed, which is r to the 4th, minus the integral of r to the 5th is r to the 6th divided by 6. This is going to go from 0 to 2. And then we're going to integrate 0 to 2 pi, that multiplied by cosine squared of theta d theta. So now I'm just focused on this part. When we plug in 2, we get 16 minus 64 divided by 6. That is the same as 16 minus 32 over 3, which is, if you get a common denominator, this is going to be 16 over 3. So our integral becomes 16 over 3, integral from 0 to 2 pi, cosine squared theta d theta, which is 16 over 3, integral of 1/2 times 1 plus the cosine of 2 theta d theta, 0 to 2 pi, and this gives us 8/3 multiplied by theta plus 1/2 sine of 2 theta, again from 0 to 2 pi, and the only thing we need to do here is plug 2 pi in for theta, and that is going to give us 8/3 times 2 pi, which is 16 pi over 3. And finally, let's go ahead and take a look at this integral. So we have the function x squared plus y squared being integrated over the region with respect to z here from the square root of x squared plus y squared up to 2, and then from here to here, and finally here to here. Now the region is this cone. We talked about that a little bit ago. And we can change the limits of this cone. Instead of putting the square root of x squared plus y squared up to 2, we know the square root of x squared plus y squared is equal to r in polar coordinates. And then from there, we're going to be integrating on this circle down in the xy plane. And that is simply r between 0 and 2, and theta between 0 and 2 pi. So this integral becomes this integral. Now I also made the substitution x squared plus y squared equals r squared, and then the change of variable gives us an r dr d theta. So this, of course, is r cubed. Integrated with respect to z is going to be r cubed times z. And when we plug in z equals 2 and z equals r, we are going to get 2r cubed minus r to the 4th. Now we'll integrate that with respect to r from 0 to 2, and then finally with respect to theta from 0 to 2 pi. Integrating now, we have the integral from 0 to 2 pi of 2r to the 4th divided by 4, which is r to the 4th over 2, minus r to the 5th over 5, from 0 to 2, and then d theta. Plugging in 2, we get 16 divided by 2, which is 8, minus 32 over 5. Integral of that with respect to theta. And if you do the math there, this is going to be 8/5 integral from 0 to 2 pi d theta, which is simply 8/5 times theta from 0 to 2 pi, or 16 pi over 5. And that concludes this video lesson.